Hello, Integrated Math 1. Welcome to lesson 4.1.1a. We're going to start digging into one variable statistics. Good times. And we're just going to start by graphically representing our data. There's so many different ways of representing a whole big chunk of data, and I like visually looking at it, right? I like being able to look at graphs and see what it looks like. That I find is super helpful. So we're going to look at a couple of different ways of doing that. Just before we get started, I just want to remind you of a couple of terms from middle school days, okay? Just bringing it back. Remember that mean means you're finding the average of the function, right? Add them all up, divide by how many there are. And remember that median means you're finding the one in the middle. You line them all up in order, and the median is the one in the very, very middle. Can you remember that? Again, this is taking it back to middle school days. So mean is the average. Add them all up, divide by how many there are. Boom, there's your average value. Median is if you line them all up in order, least to greatest, and then you pick out the one in the middle. That's going to be your median. So our learning goals over the next couple of days, we want to represent and interpret data displayed on dot plots, histograms, and box and whisker plots. If you don't know what all those are, don't panic. That's what we're going to be doing the next couple of days. We're going to determine whether a dot plot, histogram, or box and whisker plot is the best way to display a data set as well, because these are all different ways of showing your data. So we're going to decide, well, which one's the best one to use for this particular data set. So our key terms, dot plot and histogram, we are going to be talking about those today. Because we're talking about a histogram, we're also going to talk about bin and frequency. Those are going to come up as well. So you know how to represent and interpret data using these to some degree, dot plots, histograms, and whisker plots. You may have seen them before, but we're going to dig into them a little bit more, and we're also going to determine which representation is the most appropriate given the data that we have. So to get it started, we're on page M4-8. There are 4 components of the statistical process, okay? Formulating a statistical question, right? What's the question? What are you trying to find here? Collecting the appropriate data, okay? So I want an answer to this question. Let's find all the data that goes with this question. Analyzing the data graphically and numerically. That's what we're going to be focusing on. That's our big focus. And of course, interpreting the results. We're going to play with that a little bit as well. So now that I've gathered all this data and I've analyzed it, what do the results actually mean, right? What is it that I found? So right there on page M4-8, you have this great big table, and it's a big table. You can see all the site numbers here and the amount of lead in the water in ppb, also known as parts per billion. So an issue of concern for many cities is the level of lead found in drinking water, and it is a problem. We know many cities in the US even have had this problem. It's not just like a other country issue. Lead concentrations in drinking water should be less than 15 parts per billion, which we'll abbreviate as ppb. So you have our table here. The system that supplies water to a city is required to collect samples of tap water from sites it services. A water system technician went out, took samples of the amounts of lead in the water in one neighborhood in the city of Greenville, and recorded the data in the table shown. So they went out, they're required to do this testing. Technician went out, did testing at all of these sites. And for each site listed off the parts per billion of lead in the water. Now remember, it should be less than 15. So one way to organize the data in a table is to create a dot plot. Right now in the table, it's just the numbers are all kind of like all over the place. Like I can see there's some numbers too big. Most of the numbers look like it's under the 15. But a really easy way to organize data is in a dot plot. I think it's funny that we call it a dot plot because it actually doesn't use dots, it uses X's, but you get the idea. A dot plot is a graph that shows how discrete data or data that can be counted are distributed using a number line. Dot plots are best used to organize and display a small number of data points. So we're going to construct a dot plot. Let me grab my pen here. we're going to construct a dot plot to represent the amount of lead in water at each site. So first of all, I need to number, I don't need to number 1 through 20. These are the numbers I'm looking at. It looks like I go all the way up to 22. You know what? Let's go ahead and just start, and I go all the way down to 1. So let's just count starting at 1. I need to get from 1 all the way up to 22. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. So all I've done is I've just numbered the number line on our paper there. That's all I've done. Now, I'm not worried about these numbers, all right? So for a second, I'm just gonna be like, sorry, my pen's going crazy. I don't want these ones, okay? These are the numbers I'm going to mark on my dot plot. So it's real simple. I see an 11. I'm going to come over to 11. I'm going to put an X above it. Be like, cool, took care of you. I see a 22. I'll put a little X above 22. I'll take care of you. I see a 6. So I'll put a little X above 6. 10. I'll put a little X above 10. There's an 8. So I'll put an X above my 8. 3. So I'll put a little X above my 3. 12, I'll put an X above the 12. 5, I'll put an X above 5. Now watch this. There's another 10. So I'm going to put a second X directly above the 10 because I have 2 of them, right? There was a 10, there was a 10. So I have 2 X's above my 10. I'm going to have you finish this off. Go ahead, hit pause, finish this off, and then hit play when you're ready to check your dot plot. So I hope you kept going. It looks like I've got 2 4s, so 4 and 4, boom, boom. I've got 2 7s, so 7 and 7, boom, boom. I've got another 11, so I'll pop that over there. I've got another 7, oh my gosh. I have a 5, another 5. I have a 1. I have a 13, another 4. And another 7. Oh my gosh, there's a lot of 7s here. Boom. So hopefully your dot plot looks something like this. We do need to label things. So remember that these numbers were the amount of lead in the water. So we're going to say amount of lead. We're going to put that right below. And we'll just put ppb for our parts per billion. So this is how many parts per billion there are of lead in our water. This is an interesting little dot plot. Let me show you the pretty one. I'm going to erase all of this. I hope, again, hit pause if you need it, but I'm going to erase this, and I'll show you the pretty one. I'm going to erase all that. Oh, there it is. Sorry, it got all wonky. There it is. There's the pretty one. So here we have our dot plot. Hooray, you made a lovely dot plot. Good job. What conclusions can you draw about the amount of lead in the water of the neighborhood in Greenville? Sorry, I keep saying Greenfield. Greenville from your dot plot. Hit pause, jot down your thoughts, hit play when you're ready to check your work. Maybe you noticed a few things. We said 15 was the problem line, right? So maybe you noticed only one site was over 15 parts per billion. Maybe I noticed that most of them were actually below 10, that most sites had 10 or less than 10 parts per billion of lead, that it was only a few places that were over that. And again, only one site had more than 15 parts per billion of lead in their drinking water. So I would be worried about that site. The others I think were okay, but that site I'm worried about, although I might keep an eye on a couple of these that are between 10 and 15. I might want to watch those too. Now, according to the Environmental Protection Agency, if more than 10% of tap water samples are greater than or equal to 15 parts per billion, then action is required to reduce the levels. So you've gone out, you've checked all the sites. If 10% of your sites or more have too much lead, they're over that 15 parts per billion, then by law, they are required to do something about it. So according to the data in our dot plot here, is action required to reduce the amount of lead in the water in the neighborhood? Go ahead, hit pause, write it down. So how many sites did we have? I'm going to come back to the table here for just a second. I'm going to scroll back. 20 sites total. And of those, there was only one that was over the 15 parts per billion. So one of the 20 sites, I'm going to grab my calculator real quick. 1 divided by 20, that is 0.05. Whoa, sorry, my pen went funky. That happens a lot. You guys know this. 0.05. That's actually then, if I multiply that by 100, that's only 5%. Wow, my pen is having all kinds of fun today. That's only 5% of our sites that are above the safety levels. So no, we are not required to take action on this. There are 20 data points, only one data point is greater or than or equal to that 15 ppb of lead. This is less than 10% of the samples, so no action is required at this time. You might still want to take action, and my gosh, if I lived near that testing site, I would definitely be saying something. But technically, by law, they're not required to do anything about it. Kind of scary when you think about it, isn't it? So the mayor of Greenville is now a little concerned. We found a site that clearly has a problem. So the mayor of Greenville wants to analyze the lead levels for the water in the entire city. All right, we've noticed a little issue in one site in a neighborhood. So let's look at the whole city. This is the frequency table. It's what we call a frequency table. The frequency table displays the data for the amount of lead in drinking water samples taken from sites all over Greenville. Now, when we talk about a frequency table, this means there are 32 sites that had 0 to 5, that their level was from between 0 and 5. There were 48 sites whose level was between 5 and 10. There were 100 sites whose level was between 10 and 15. 47 sites with a level between 15 and 20, and 23 sites had a lead level between 20 and 25. It's a little scary. So this is why we call it a frequency table. This just tells us how many sites fall into each category. And in fact, we have a name for those categories. You ready? These categories are what we call bins, okay? A bin represents an interval of data. So instead of like 0, 1, 2, 3, 4, 5, no. We're just going to have one bin where everybody that's between 0 and 5 goes into that bin. So these little categories that we have here, we refer to these as bins. Okay? Does that make sense? So we did a dot plot for our last one, but now we've expanded it to the whole city. And we have way more data now. Look how many sites. We had 20 sites before. Oh my gosh, we have way more than 20 sites now, 32 and another 48 and another 100, another 47, another 23. We have way more than 20 sites now. So a dot plot isn't going to be real useful. It would be way too long to try to plot all those out on a dot plot. So another way to display quantitative data is to create a histogram. So if you have a lot of data like this, we call it quantitative data. But if you have a lot of data, a histogram is much easier to use. You probably know a histogram better as a bar graph, okay? A histogram or bar graph is a graphical way to display quantitative data using vertical bars. It shows how much data is in each bin. The width of a bar in a histogram represents the interval of the data and is referred to as the bin. So how wide your bar is, that's your bin. Okay, everybody from here to here. Yay. The height of the bar indicates the frequency, which is the number of data values included in any given bin. So the height of your bar depends on how many items are in that bin, and we call that the frequency. So these are my bins. This is my frequency. This is the number of items in each bin. Now, histograms are effective in displaying large amounts of continuous data, or data that can take any numerical value within a range. So we really like using histograms if we have a lot of data. Guys, we have a lot of data. So we're going to go ahead and construct a histogram. You ready? You can think of this as your x-axis. You can think of this as your y-axis, okay? Very similar to what we've done in the past. So I'm going to make my x-axis. I'm going to make my y-axis. Let's see. It looks like I'm counting by fives on my bins, right? 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25. So I'm going to count by fives for my bins. So 5, 10, 15, 20, 25. Now, for my y-axis, for my frequency, I need to make sure I can get all the way up to 100. So I'm going to make sure that I have 100 at the top, that I can get all the way up to 100. And that means halfway. That would be what, 50? So you know what? We could probably count by tens on this, right? So 10, 20, 30, 40, not my best ever, 50, 60, 70, 80, 90. Okay, not as evenly spaced as I would have liked. Hang on, I'm going to try to fix a few of these because those went weird. 10, 20, 30, 40. There we go. That's slightly better. So 10, 20, 30, 40, 50, 60, 70, 80, 90. And we did get all the way up to 100. Just got to make sure we get there. I do want to label stuff. Remember that our bins, these are the amount of lead in the water in parts per billion. So I'm going to make a little note here. Amount of lead. And we said that was in parts per billion, ppb. This is our frequency, but if you recall that this is the number of sites, right? 32 sites were in that bin, 48 sites. So I'm going to say number of sites. I'm going to grab another color to help emphasize what I'm doing here. So here we go. We said the height of the bar is how many things are in the bin. Well, from 0 to 5, so my bar is going to go from 0 to 5. And the height is going to go all the way up to 32. So, oh dear. So we're going to go all the way up. There's 30. Oh my gosh. A little bit past that to get to 32. And then we'll come on down. So I've made my first bar. And I can color it in. Yay. So 32 sites fit in that first bin. Site from 5 to 10, I had 48 sites. Okay, so from 5 to 10, there's the width of the bar. And I want to get all the way up to 48. So I don't quite get to 50, though I get close, don't I? So just a little under 50, and I'll make my other bar. So there are 48 sites now in that bin. Yay! So there's my second bar for my histogram. My third bar goes from 10 to 15, 100. Oh my gosh. So this one has to go all the way up, all the way up to 100. Go ahead and hit pause. Oh my gosh, my bar is going crazy. It got a little wobbly there. It was just a big bar. Can you go ahead and hit pause, finish the histogram, hit play when you're ready to check your work? So hopefully by now you finished it. So 47, again, that puts us almost to 50, not quite, but pretty close. Ooh. So we'll come on down, and there's my bar. So 15 to 20, we had 47 sites. And from 20 to 25, we had 23 sites, so a lot lower. So we're going to come up a little past 20, roughly. You can see why graph paper might make this a little easier to work out, although we did okay. We did okay. So here's your lovely histogram. It's so beautiful. And definitely a little easier than a dot plot. I love dot plots. I think they're really cool to be able to see the distribution. But with just this many sites, We would have literally done hundreds and hundreds of X's on our dot plot. I don't want to do that. So since there's so much data, a histogram, way better to use. And it's so pretty. In fact, I'll show you the official one. Here we go. Ooh, isn't it pretty? It's so pretty. So what conclusions can you draw from the histogram about the amount of lead in the drinking water of Greenville? Hit pause, jot down your thoughts, hit play to keep the discussion going. So just make a quick mental note for myself here. Let me grab my red pen. It's a little bit easier to see on that green. I just want to make sure I got my numbers right. So we said that was 32, that was 48 sites, 100 sites, 47 sites. And what was that last one? Was it 23? Yeah, 23 sites. Okay, 23 sites. So I was looking at this, and there are a lot of conclusions I could come to. First of all, I know that 15 was the key, right? So I added these up real quick. 32 plus 48 plus 100. If I add those up, I realize 32 plus 48 plus 100 means that's 180 sites. So I can see that 180 sites have less than 15 parts per billion of lead in the drinking water. But if I add these up as well, that 47 plus 23, these sites are over, right? So 47 plus 23 means I do have 70 sites that have 15 parts per billion or more in the drinking water. Yikes. That's a little scary. That's a little scary. I think we're going to skip this problem. If you're dying to do it, it's there. But we're going to skip that for now. So remember what we said earlier about the EPA, how if you have 10% or more of your sites are over, you have to do something about it. Look at what we just wrote about how many sites were under, how many sites were over. Is the city of Greenville required to take action to reduce the amount of lead in the water? Hit pause, do a little bit of work, and then hit play when you're ready to check your work. So we said that there were 180 sites below, plus another 70 sites that were above. So that means altogether, if I add those up, I've got 250 sites. But 70 of them are over. So I'm going to do just a little bit of math here. 70 divided by 250. Thank you. I need a calculator for this. 70 divided by 250 is 0.28. If I multiply that by 100, oh my gosh. Oh my gosh. Whoa, 28% of our sites are over the safety levels of lead in the water. That is way more than 10%. So let me erase this. Yes, according to the histogram, 70 of the 250 site samples have 15 parts per billion or more of lead in the drinking water. That's 28% of the sites. This is much greater than 10% of the sampled sites. So, oh my gosh, yes, action is required here. My goodness. So just your own thoughts here. Do you think that this histogram was a good representation of the data? Hit pause, jot down your thoughts, hit play to keep the discussion going. So I felt like this was a pretty good representation. There is a large number of data in our, I can say this. I think this histogram was a good representation of the data because there's a large number of data points given in the intervals. And the intervals are broken up enough to allow me to easily see. Especially, I really wanted to make sure I could see that 15, right? Who was over the 15, who was under the 15. My data was broken up evenly, right? I had nice even bins that made it much easier to see what's going on. So I feel like this was a pretty good histogram. It really definitely gave us a good idea of what's going on with the lead in the water at these sites in Greenville. As always, guys, I hope you found this helpful. I hope you found this useful. If you have questions or concerns, come talk to me. I'm around, and I'll see you guys soon. Bye.